Hello everyone. In this video, I'm going to walk you through these questions. Question 15 of part 1 of the ROF technology homework exercise. The question asks you to design the um, open circuit stop-based microstrip trapezoid low-pass filter that satisfy the following conditions. Following specification. The cutoff frequency is 10 GHz. The ripple in the passband is 0.1 dB. The attenuation in the stop band is 30 dB. And the stop band frequency is destined to be 20 GHz. And the question expects you to implement the filter in Roger Gilroy 4003C, where the dielectric constant is 3.55 and the thickness of the substrate is 1 mm. Now, I've changed the question slightly. The thickness, the question, this question is actually taken from the internet, but I have resolved it and changed some of the parameter, including the thickness here. The loss tension, for example. So, first of all, they ask for trapezoid low-pass filter. You need to find out the order of the filter according to the formula specific to trapezoid. So, first of all, we need to write down this parameter first. So, I'm going to switch over to the whiteboard. So, you're now looking at the whiteboard. Now let's write down the parameter first. We are now looking at Q15, question 15, and the part 1 of the ROF technology exercise. The cutoff frequency is 10 GHz. The stop band frequency is 20 GHz. The ripple in the passband is 0.1 dB. The uh, the loss, the stop band loss is 30 dB. So I use it. I use gain here to represent it. Actually, you don't need to worry about that. And the characteristic impedance, the reference impedance is 50 ohm. So first of all, we need to find the order of the filter. We are going to use this formula. Then A over 10, or actually AS, minus 1, and then 10 allow minus 10 minus 1, and then A cosine Fs Fc. So we are going to substitute the parameter according to what we have got from the questions. A cosine, and then 10, and then here is 30. So we write down 30, and then 10, 0.1 divided by 10 minus 1, and then A cosine 20 divided by 10. So if you do it correctly, you will get the answer 4.576. Of course, we need a digit. So what you need is we use F20 to be 5. So the order of the filter is 5. So the next thing that you need is to use the prototype table to find out the gain in each stage. And according to the table, what I found was G1 is equal to 1.4, sorry, 1.146A. G2 is equal to 1.3712. G3 is equal to 1.975, and then G4 is equal to 1.3712, and then G5 is the same as G1. So it's symmetrical. That's what we get from the prototype table. The next thing is to establish the starting topology for the filter. So first, I'm going to G1, we have two options. We can use either this one, so G1, G3. I think we just stick to this version. G5, and then G2, G4. So this is the basic low-pass filter topology. Alternatively, you can also, sorry. So you can have another topology as well, but I chose to use this one because we have less less procedure to resolve. Uh, the next thing that you need is a procedure, so-called Ritras transformation. In this step, you are going to replace or the inductor with a short circuit stop with the stop length 45 degrees. So you will get this. And this. The length here is 45 degrees. And you are going to replace all the capacitor with open circuit stop. So here, 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 and now we are going to find out the impedance for each of the stop section. For G1, G2, and G4, the impedance is going to be 1.3712. So this one 1.3712. For this one, it will be 1 over, yeah. So this one 0. This one originally it was 1.14. The gain is 1.1468, but you need to 1 over it. 468. So from here, I can say here is 0.872. The filter should be symmetrical. So this one is also 0.872. And this one here is 1 over 1.75, which is equal to 0.506. So we got all the impedance using the method to call matrix transformation. We transform all the things into the respective impedance. Let's label this one. This one is Z1. This one is Z2. This one is Z3. This one is Z4. And this one is Z5. Now, there's something challenging here. There's something challenging here. First, the question dictates that you have to use open circuit stop, but we have two short circuit stop. All the inductor will end up with short circuit stop, and these are the two. This is one of the reasons why we choose this topology, because we have only two inductor. The other has three inductors. But fortunately, we have a way, we have a process, so-called colloidal identity. Colloidal transform. So what are they? They are the method that can trace the short circuit stop into open circuit stop, and the other way around. For example, if you have a open circuit stop here, the open circuit stop is has an impedance Z2, and the open circuit stop is based on a transmission line with the impedance Z1. You can immediately transform it into another transmission line with different impedance and a short circuit stop. And the impedance here is N square divided by Z naught 1. And this one, N square divided by Z naught 2. And what is N square? N square is 1 plus Z2 over Z01. So this is one of the transformation pair you can make use of for this question. Another transformation pair that you can make good use of is to transform all the short circuit stop into open circuit stop. So for example, now I'm going to save some space. If you have something like this, so you have a short circuit stop, and in the short circuit stop, you begin with Z naught 1, and then the main line is Z naught 2. You can immediately transform it into a line and then a transmission line. So it's an open circuit stop. The impedance here is N square Z02. And the impedance here is N square Z01. And what is the N square? The sum. The sum, yeah, N square is equal to 1 plus Z naught 2 over Z naught 1. I mean, this Z naught 2, this Z naught 1. Okay? So we have got two pair here. Now we are going to start doing something. So for this circuit, we have to get rid of them, but it's difficult. What we can do is you can add a dummy transmission line section with characteristic impedance 1. The length here is 45 degrees. And you are going to do the same in here. By adding these two transmission line sections, you are not going to change the characteristic of the filter. But now, if you take a look here, you have a open circuit stop together with a transmission line section with characteristic impedance 1. So this one is very similar to this. So immediately I can transform it. So first I'm going to clean out here. So we can rewrite it. And this is V2, V4, 1.37 12, 1.3712. So we have this one here. This one will remain unchanged. Now, I told you this one is going to, yeah, under the assumption, under the knowledge we have gotten from here. We can change it to here. Yeah, this group. This group here. We can use this identity to change it to a short circuit stop. Now the impedance here is, first of all, we need to calculate n square plus, so Z2, which is this line impedance, 0.872, and then Z01, which is 1. So from here, you can get 1.872. So this guy here, if you do it carefully, you got a transmission line here. The from what I can calculate, this one according to here is n square over Z02, which is 1872 according to here, and Z02 is the original value in here, 01. So if you do it very carefully, um, 2. Yeah, I make a mistake here. Yeah, this one should be Z02 divided by n square. This one is Z01 divided by n square. So based on this knowledge, so unite n square. So it is 0.4658, and this one 0.5342, and this one will be the same, 0.4658, and you follow the by a open circuit stop will be exactly the same. It's very easy, but if you are clear, your mind is clear, it's very easy to handle. So it looks worse. We end up with 2 more inductor, 2 more short circuit stop, but don't worry. This is the law. Actually, this is the way to path to something doable. Originally, it's very hard, but now it's getting downhill. We have one more inductor, but on the other hand, it's very easy to handle. So what you need to do is to look at this box, these two pair, and obviously you will take care of these two as well, and focus on this uh, transformation pair. So you have one short circuit stop together with a uh, transmission line. According to here, you can change it to a transmission line and then followed by a open circuit stop. So we just do this. So this one will end you up with the main line will not be changed. The one here will become a block of transmission line and then followed by another open circuit stop. And from what I can get here is this one is n square is equal to 1 plus um, um, 0.4658 divided by 1.3712. So you get 1.3397. And with this, you just substitute to here, and then the value here times this one. And if you do it correctly, this one will become 1.837. And this one here will become 0.6240. So you only have one left. So this one will remain the same. And it's symmetrical. It's symmetrical. So you don't need to worry about that. And here, obviously, it will be symmetrical. And the impedance will be the same. So what can you do now? You still have to resolve this. Uh, you still need to eliminate this short circuit stop. One way you can do is you can add one more line section with 50 ohm without changing the behavior of the circuit. And the length of this line segment is also 45 degrees. And same here. So if you do that, I need to free up some space. I need to free up some space. So I will keep some notes here. I don't need this. Okay, we are back now. Sorry for the delay. Okay, we still can make it. So this is the last thing that we continue. We try to continue, yeah. So what you can do is you use the same technique as you did. You add one more block here, then afterward, the block will become something like this. But then you can change it. So we don't really need this. So this guy here can undergo another transformation to end up with a transmission line together with an open circuit stop. So I'm going to write it down here. So this one here will become another open circuit stop. The other will remain unchanged. So this one is 0.624, and here will be 1.837, and here is 0.506. This is Z3, and here is 1.837, and here is the same 0.624, and here so we are going to change this. Yeah, you will change this, you should automatically change this as well. So this will be like this, and this will become another open circuit stop. Now we are going to calculate the length of the open circuit stop, the impedance of the open circuit stop. And according to what we have here, n square now is equals to 1 plus the ZO2. This means 1, and then divided by 0.5342, and this will give you 2.872. And with this, you do a little bit of calculation on the file. This one, n square times 1. So this will be 2.872. And this one will be n square times this guy, 0.5342. And if you multiply carefully, you will get 1.534. So this is your answer, 1.5342, and this one you just copy. So basically, you have already achieved the most important part for the question. Most likely, if you have any examination question, most likely, uh, you just need to achieve here. You don't really need to carry on, but you still need to denormalize it. All these are normalized value. To denormalize it, you just multiply each raw figure here by 50. So if you do that, what you will get here is, let me do more cleanup. So I'm going to denormalize it. So the first segment may be 1 for the transmission line, for the in-output port. So it will be 50, and then there will be an open circuit stop. And this one will be 2.872 times 50, which is 143.2. And then followed by this one. I'm not going to go through all the calculation with you, but I've already pre-calculated. So another one, after denormalization, then you get 722. And this one, 91.85. And this one, 25.3. All this figure here represents the impedance, and this will be symmetrical. This one, 70.1, 143.6, and 50. So this is the transmission line that look like this is the kind of solution that appears to be in the printed circuit. But the question asks you to implement this circuit um, in Roger Gilroy. So what can you do? One of the way is instead of going through all the formula, you can use the line calculator function in another software. So before doing anything, right, let me just do a little bit of cleanup. Do more. So I managed to free up this one. So let's suppose uh, this is line 0. This is line 1, line 2, line 3, line 4, line 5, line 7, line 8, line 9, 10, 11. So you can use the line calculator to handle this problem. Before doing anything, I will show you, um, I will share the screen with you. So this is the so-called line calculator. In the line calculator, you can actually enter the impedance value. For example, the first one, line 1, line 0 is 50 ohm. So you can just type 50 ohm here. And remember the length of the line, 45 degrees. And also the frequency, 10 gigahertz. So by doing this, you automatically give you the width and the length. So I'm going to write down this value. So line 0 and the characteristic impedance 50, width and length 2.327, 2.25. So they are in mm. So you can use this way to work out the line impedance instead of going through all the calculation. If you change the value here to 70, 143.6, then automatically, yeah, of course you need to take care of this as well. Automatically you will get uh, the value of the width 0.16 and 2.45. So you can continue with this process until you get everything done. So I'm not going to go through every figure. This is one of the easy way, and I'm going to switch you back to the right board. If you do it very carefully, you will get line 1. I've already entered the value here. 2, 3, 4, 5, and this one is going to repeat. Yeah, 6. Anyway, this is what I get. Oh, 965, 2.34. So if I do it carefully, 2.33. And this one, the width is longest, 4.664. And this, 25, 31.2. So you can just keep going. Eventually, you end up with a table. And I'm not going to do everything for you, but the methodology is the same. Anyway, if you have further questions about the methodology, please leave your question to the comment section. Uh, Otherwise, thank you for your attention. Okay.